So going back to here, this is the think about the sort of basic plan or goal of a factor analysis is to take a bunch of data that we have, where we have individual respondents to a number of items on a scale of some sort. We then take those variables and make it into a correlation matrix. So it's variable by variable, k by k. And then once we have that, the goal is to try to explain these 1 through k variables with as few factors as possible. Right, so we're trying to reduce everything down. So we have k variables, and we want to try to explain them with j factors, where this j should be far fewer than this k. All right, now it could be that you have, 5 variables and you want to explain it with 1 factor. Because you think it's just one, it's a unidimensional sort of factor, it's just one thing, all the items are related to each other for one reason, under one dimension. But more than likely, you have more, like 20 items, 20 individual questions, and you want to explain them with something like 2 or 3 or something factors that represent different subscales within that, within those items. Once we actually figure out the variables are down here, so this is 1 through k, and this is the 1 through j factors, and these represent the loadings. Those are the correlations between each item and the factors that we extract. If we take that matrix and multiply it by itself as a transpose, that should recreate the original correlation matrix. This is what's called the reproduced correlation matrix. It's the correlation matrix that is a product of the loadings and the factors that we've extracted. The idea being that if there are really, j number of factors that are driving the responses to the items, then by using those j factors, we should be able to recreate this pretty well. The closer the reproduced matrix is to the original matrix, the better our factors are doing. And we can look at that by taking our original, subtracting out our reproduced matrix, and what's left is something called the residual matrix. If everything in this residual matrix is 0, then our reproduced matrix sort of perfectly captures the original matrix. The easiest way to make sure that your reproduced matrix is identical to your correlation matrix, the original correlation matrix, is to set j equal to k, meaning that I'm going to extract the same number of factors as I have items. If I do that, it's just resorting, reconfiguring the data into the same number of factors. That's completely boring. It's like I'm explaining k things with an equal number of things. We haven't reduced anything, but that will perfectly reproduce the matrix. As j starts to become less than k, we're not going to reproduce it perfectly, but the goal there is to sort of get as close as possible to make that residual matrix as small as we can while retaining only as few factors as we need. To take a closer look at this factor loading matrix and what's going on there, and I showed you a little bit of this in the lab on Tuesday, that if you square and sum across the loadings, you actually then are getting the commonalities, and that's how we sort of compute them. Commonalities are the sum of the squared loadings, and I do realize that I'm not consistent in how it's spelled. Here I have commonality, and in other places it's communality with a U. I'm actually not quite perfectly certain which one it is, whether it's a U or an O. I've seen both used. They sort of, apparently, in my brain, I flip-flop back and forth. It makes sense that it's commonality because it's talking about common variance, but I've also seen it as with a U, so I don't know. If we square the loadings down the items, we actually can get the eigenvalues, or at least the reproduced eigenvalues for each factor, telling you how much each. So this tells you the percentage of variance in an item explained by the factors. going this way, this tells you the total amount of variability that factor is explaining in the data. So this is about the amount of variance in the item. These are about the amount of variance in the factor. All right. So now let's go on this stuff. So we're talking about extraction. There's really two big steps, right? Two big steps to factor analysis. You got to extract them and you got to rotate them. That's typical. You're going to see those together. You almost never see extraction without rotation. And you're definitely not going to see rotation without extraction. So extraction means sort of deciding on a couple things. What is the method that you want to use to extract? And what is the and how many factors you're planning to extract. So it's both of those, method and number. The method has something to do with deciding things like, are you going to do a principal component analysis or a common factor analysis? And then if you're deciding on common factor analysis, what type? Because there's something called principal axis factoring, there's maximum likelihood factor analysis, there's image factoring, alpha factoring, there's minimum residual, there's generalized least square, there's a bunch of different ways in which factor analysis can be done, and almost every one of those, I'm pretty sure every one of those, differs in how it's trying to estimate the commonality. So what's the big difference we talked about before is that PCA doesn't try to estimate the commonalities first. It assumes that all variance is common, which is a weird thing to assume. It's basically saying that not only are all the items perfectly reliable, like a reliability of 1, but that all the variance in that reliable item relates to the factor. All right, so PCA is one method, and it assumes that like 100% of each item is common, has common shared variance. And then as it goes through the process, as it sort of cycles through the sort of factor analysis one time, it then estimates those commonality values from it. All right, so we assume everything's common, we run through it, we actually get the loadings, we square and sum them across, and then we estimate our commonalities. Factor analysis of every sort does not assumes that the common variance is far less than 100%. You know, it's like, all right, it's not making this ridiculous assumption that 100% of the item is common. It also doesn't assume that it's perfectly reliable. It starts off saying, look, we know there's going to be unique variance in these items, but we have to have something to put into the matrix to actually to assess, to do that. So what it does is it tries to estimate. It tries to estimate what the commonalities are first. So first we're going to estimate the commonality. We're going to cycle through the whole process of the factor analysis. And this actually is going to do, unlike this will happen one time. This happens once in PCA. In factor analysis, this is going to be, I'll just put this is going to be iterative. It's going to do it multiple times until it converges. It's going to iterate over and over and over again. We're going to put an estimate of the commonalities in there. It's going to do the factor analysis. It's going to then square and sum the loadings to get a new estimate of the commonality. And then it's going to put it back in again. And then it's going to go through the process again. And then it's going to put it back in again. It's going to keep going back, all the way back over and over again until you reach something called convergence, which means that the estimates you put in are the same as the estimates you get out, and it sort of stops sort of changing. At that point, then, it spits out the new commonality estimates. So I'll say this is like the estimate of the commonality, and then these are the sort of the final sort of calculations of commonalities based on the final converged model. So where it says FA refers to a whole mess of methods, the methods differ on this part. How do we estimate the initial commonalities? Those initial commonalities get estimated in different ways. If it's principal axis factoring, maximum likelihood, minimum residual, all those things are done differently, and that's what actually drives the differences in the method of extraction. So PCA says 100%. All the factor analysis estimate something here. For instance, the one that's used often is we're going to use the squared multiple correlation. Right, so if we do that, that's something called principal axis factoring. Principal axis factoring uses the squared multiple correlation of each item predicted by all the other items as the estimate of the initial commonality. It iterates through a bunch of times, and then it converges on the actual commonality value that comes from the model. So, and that's a lot to sort of take in. I get that. I'm not expecting you to sort of understand everything I just said, because we're going to talk more about it. But the big difference between PCA and FA is 100% of the item is common versus that's ridiculous, we're not going to do that. We're going to try to estimate it first. And that's the big difference. And that's why PCA is sort of seen as much more sort of descriptive, exploratory, because it has sort of a ridiculous, overestimated sort of assumption to begin with, where factor analysis tries to do a better job of estimating it first before sort of iterating through. This does it one time. You get one shot. It goes through once, and you get commonalities. Done. There's no iteration. There's no putting it in back and forth. That's it. With all the factor analyses, there's an iteration process. We estimate it, and it's supposed to then give you a better, more accurate estimation of this. And if you have a decent correlation matrix and everything sort of works out okay, it probably doesn't make a big difference which type of factor analysis you use. Maximum likelihood, principal axis factoring, all those, you should get a pretty similar result in the end. So oftentimes it doesn't make a huge bit of difference which extraction method you make, but sometimes it does make a huge difference depending on certain properties in your data. But that's sort of beyond, that's getting into the weeds. Once it does this, sure, what's up? It is definitely 100% PCA, because you can even tell, because that was the whole reason we talked about, where is it? Like here, this differentiation between principal, for factor analysis, principal components is here, common factor analysis here. You're actually trying to estimate the common variance first, and that's what makes it a sort of common factor analysis, or principal components analysis is much more sort of descriptive in its sort of use, because it's going to overestimate everything. I was trying to think of where I would have said that on this slide, but sorry, I don't know. No, I mean, not necessarily. So I can see where you think that, and people oftentimes do that. Well, they will do a PCA first and then move to a factor analysis. You don't need to do that. If you have some idea about how, so for my personal opinion, okay, this is my take on this whole thing, and you're going to find people that are going to disagree. I don't like PCA because it's going to overestimate everything, and it's a sort of one-shot deal that doesn't, where the assumption seems sort of ridiculous. You're literally assuming that to start off with 100% of the item shares variance with other items, which is never going to happen. And then it sort of spits out to you what the commonalities are from that. I think every time someone uses a principal components analysis, they end up overestimating the loadings, overestimating the number of factors, overestimating everything. Now, from a purely sort of exploratory viewpoint, if you don't know very much about the data you're using, and you're really trying to get an idea of what's going on, it may actually be a good idea to over-extract, to actually pull more things out to sort of play with than is really there, with the idea that you're going to confirm and do more stuff later on, do a factor analysis on a second set of data. So it's not like you're going to do a PCA and then have that inform the factor analysis in the same data, and then move to a confirmatory factor analysis in the same data. That would be 3 different data sets, or 3 different analyses. Right? Principal components analysis could be done super early on if you know very little about the data. Exploratory factor analysis would be done if you know a little bit more about it, and you actually, at least have an idea of how many factors to expect. But even then, the reality is, based on what we know now, the kind of software that we have now, and the computing power we have now, most everything could and probably should be done as confirmatory. because you know the items that are supposed to go on which factors. It was probably developed specifically to work that way, so why aren't you just trying to test it instead of just exploring as if you don't know anything? So there's a bit of a weird transition that we haven't quite made yet, where people still use a lot of exploratory factor analysis when they in fact should be doing confirmatory. And that's just, I think, because it's just like with the ANOVA, it's just like what people know. People know exploratory factor analysis, so they continue to use it. And the availability of it in SPSS and SAS and other programs like that, where you'd have to go to a different type of program, like AMIS or something, if you want to do a confirmatory model. So I don't know, there's just a weird thing that hasn't quite transitioned. I can argue that every factor analysis is in fact truly a confirmatory factor analysis, but people just don't do it that way because they think it's easier or something, I don't know. But to reiterate what your question, it is definitely PCA is the one-shot, sort of more descriptive approach to trying to find underlying constructs. And factor analysis is more theory-driven, it's iterative, it requires you to make some kind of estimate of what's going on to start with. You may or may not have heard the term like start values. You got to have start values for it to sort of begin and then iterate through. And that's where this first estimation process comes from in terms of getting what the starting values are. Where should we start? What are the anchoring points that we're going to put in for the commonality estimates before we go through, iterate, and actually try to estimate the real values, or at least the values from the data set. And so if I said it the other way around, which God, I hope I did not. Now as soon as I get home, I'm going to be back watching the video over again, because that would have been it's almost like from my perspective as a psychometrician, saying that confusing like the God and Satan, flipping them around, saying that they're the other way around. It's like just a thing you wouldn't do if that's your belief system. Like, I don't know. So if I said that, holy shit, I got to go back. I guess I need to repent, do some Hail Marys or something. I don't know. But because I definitely angered some kind of psychometric God of some sort. But hopefully I didn't. And we'll go back and confirm that or something. So I'll definitely be watching that video later on. That's sort of the good and the bad of recording everything that you do and say, is if you do say something wrong, it is there, recorded, and you can point at it and say, yep, you screwed up. But let's go forward with that in mind, that this definitely should be this way, not the other way around. Once you actually extract in this sort of two-part process, which is one, what are we going to use to estimate the commonalities? Because so we haven't got to the sort of details yet, but this is going to impact, if these estimates are larger, it's possible you're going to be extracting more factors. If they're smaller, you may be extracting less factors because there's less sort of variance shared to sort of pass around through more factors, right? So this can impact your choice of extraction method. Can impact the number of factors that you extract. Now, I'm going to argue that in most cases, using PCA will lead you to more factors than using FA. You're going to extract more factors because the mathematics behind it actually assumes that there is more shared variance. So it's trying to explain a larger amount of variability with the factors than if you actually start off with some estimate that's lower than 100%. So not only do you start off with more factors extracted, the loadings are also going to be overestimated, or at least larger than they would be had you used a factor analysis method. All that being said, once you choose a method to extract, you choose the number of factors to keep, like how many you're going to extract, what you're going to get back. You're going to start getting things back, like you're going to estimate factor weights and loadings, just like you did with canonical correlation weights and or canonical coefficients and canonical loadings. Same idea. The factor weights are used to create factor scores. Factor loadings tell you the relative importance of each item to the factor. And that's how, using the loadings are how you're going to interpret what the factors are actually doing and how to sort of, how to view them, how to interpret their meaning. So these are like, factor scores are like canonical variate scores. Loadings are loadings. They're the same thing, whether it's canonical correlation, discriminant function, factor analysis, we interpret the same way. It's a correlation between the item and that factor, function, variate, whatever it is. Factor weights you use to get factor scores. What else? Rotation. Let me actually erase this stuff. Rotation is another process that really comes down to the fact that as items are, as these sort of vectors in the eigenvalue decomposition are being projected into space, the first one that gets projected really is the one that sort of decides how the rest of them get put into space, right? Because so as the first factor gets spit out into space to try to explain the most variance, all the other factors are going to be orthogonal to that first one. Doesn't necessarily mean they're going to be interpretable in that original form. So what typically comes, by typically I mean it will, like it is done as part of the process. We will rotate the factors to try to increase its interpretability. Now there are some rules to that in terms of how do we decide which way to rotate and how far. But it basically, rotation mathematically converts loadings of factors so they're easier to interpret. That actually helps them make more sense. So the two general types, orthogonal and oblique. Orthogonal rotations rotate factors independently. So remember, so imagine we have a bunch of data points, and our first vector, gets put through those points, wherever those points are, gets put those points. So this is sort of factor 1. Factor 2 is going to be spit out orthogonal to the first one. This is how the extraction is going to happen. No matter what you do, it's going to happen this way. The factors are going to come out orthogonal to one another because that's how the eigenvector deconstruction works. With orthogonal rotation, if I try to rotate this factor some amount, this factor is going to be rotated the same amount. It keeps them perfectly orthogonal. They start off orthogonal, and you rotate them in a way that keeps them orthogonal to each other. And when you hear orthogonal, when it comes to sort of geometry, it means they're at right angles, right? But more so than that, it means that they don't share space. So if you think about the space in here, right? Factor 1 and factor 2 do not share this space. They're staying at perfect right angles, so everything's moving as you're rotating one factor, right? The other factor is sort of rotating the same amount. They're staying perfectly orthogonal no matter how you rotate them in space. Doesn't matter which way you rotate them. Those two factors are going to stay orthogonal. That's orthogonal rotation. That means it also keeps factors independent. It makes it easier to interpret if that works. If it works, and it actually helps to get you something like simple structure, which we'll talk more about in a second, then orthogonal rotation is preferred because it's less complicated. Now, the problem is, is in the back of your mind, hopefully you're maybe already thinking, if you're trying to identify factors or subfactors of an overall scale, where those subfactors are measuring similar things. Like if you're trying to do an overall depression inventory that has, say, 5 subscales or 5 subcomponents of depression, you're probably going to expect that those factors are going to be related. They're going to actually correlate. So keeping them orthogonal may be sort of ridiculous. It may not be theoretically feasible. So there is oblique rotation, which means the factors allows the factors to correlate. And to draw a picture of that here, I'll use a different color. So that means that I can actually rotate this factor sort of independently of the other factor. The factors actually are rotated almost sort of individually, and it sort of allows, actually green and yellow look the same, don't they? Can you tell the difference between those two? This up here is green, and that's supposed to be yellow, but they look the same. Let's try a different color. Maybe orange would be different. I can actually rotate the two of those sort of independently of one another, so that what starts to happen is you might have factor 1 and factor 2 now. So if factor 1, say, maybe stays the same, and I rotate factor 2 independently, I may actually have factor 2 may end up here or something, where now factor 1 and factor 2 are sharing the same space and are now correlated to one another. They're actually now at something less than right angles. There's an acute angle between the vectors out in space, and they now are sort of sharing space, and then to try to interpret that becomes a little trickier, becomes a little more complicated. Okay? So orthogonal keeps everything independent, makes it a little easier to sort of deal with the interpretation of things. Oblique rotation allows the factors to correlate and share space, but it actually may lead to a better simple structure, because in reality the factors should share space, and that's sort of part of the deal. All right, so factor analysis, part of the goal of factor analysis, something called simple structure. You're trying to interpret factors, so I'm trying to get meaning from what these factors are doing and how they're driving items. So simple structure is this idea that every item should load on one factor and one factor only. So that's nice and clean. So here, like items 1, 2, and 3 all load on factor 1, and that's it. In exploratory factor analysis language, that really would be that these 3 have loadings that are large on factor 1, and all the other loadings and other factors are small, like under 0.3 or something very negligible. Okay. In confirmatory factor analysis, we would actually assume that all other loadings would be 0. So these loadings exist. Everything else, like going from factor 1 to factor 4, that's actually 0. Exploratory factor analysis is not going to be 0, but it's going to be something small. So this is, if this comes out this way, this is simple structure. These 3 items load on factor 2, and that's it. Here you have something that's not simple structure, because anytime you have something called a complex loading, where item number 3 here loads both on factor 1 and factor 2, right? So this actually represents a representation of an item loading on both factors simultaneously. It's a complex loading. So when you're trying to interpret how this factor is different than this factor and trying to differentiate them, this item loading on both makes that very complicated, because it somehow is informing what factor 2 and factor 1 are at the same time, and it makes it difficult to get an interpretation where this factor and this factor are separate, regardless of whether or not you're doing a oblique or orthogonal rotation. This item makes any interpretation of the factors sort of more complex. It makes it nearly difficult or impossible to really interpret, because why is that item sort of loading or indicating both those factors at the same time, if they're 2 different factors? But that does happen. Sometimes it's because the item really does sort of relate to 2 factors at the same time. Other times it's because there is common wording or other things or content in the item that may make them relate to both factors, and it's a whole other like advanced topic of how do you avoid some of that stuff. But I'm not going to have time really to get into that sort of thing. But so what are we assuming? I think I said this before. But it's worth sort of reiterating. Anything that would affect correlations is going to affect factor analysis, right? So it assumes that the correlations are reliable, that they're sort of consistent, they really reflect what's really going on between the items. Any outlying or missing data is likely to affect the correlation. It's actually, if there's an outlier, you may be skewing the correlation sort of higher or lower than it's supposed to be. Missing data may cause things like truncation, where there's a certain subpopulation that's missing, not represented. You may actually be over or underestimating the correlations because of that. And you also just, in terms of power and things, any missing value, if you're using like listwise deletion, may reduce the sample size. The thing that is sort of the hardest thing about factor analysis and a lot of these sort of latent variable models is that they are large, they require large samples. And that's because you actually want the relationships to be stable. You want there to be a stable correlation. You want there, the correlations to reach a reliable sort of level. So that's what it says. Correlation, if the correlation is reliable, if you have reliable correlations, the more reliable they are, you can actually get by with fewer subjects. Meaning that if it's something that's a pretty stable, reliable correlation that shows up across every time you go to study this particular relationship, it comes up in this fairly stable, steady amount. Then you probably don't need as many subjects to do it. But because you need enough subjects to get a stable estimate, it's likely you're going to need more subjects to get that stability. And the more items you have, the more subjects you're going to need to sort of find it. So larger data sets with more items, more complex, larger scales are going to need more subjects. And that's because the more parameters you're trying to estimate, more things, like the more loadings you're trying to estimate, the more things you're trying to estimate in the factor analysis, the more people you need to try to estimate them. You want items that are correlated, but not multicollinear. And that's a sort of a tricky fine line. They should be related to each other. You actually want them related pretty highly, but they can't be too related, like in the 0.9, point whatever, because then they're redundant and it starts to sort of lose its appeal. So you want them to be related to each other, but not too related as to be sort of redundant, and that'll cause other issues with factor analysis. Things like doublets and what they call issues with, I'm forgetting the term. Local dependence is the term. Again, these are sort of more advanced sort of ideas. So, but that's an interesting idea. Local dependencies are something you want to avoid in factor analysis, but that's beyond this particular course. And we will talk about local dependence and stuff in 534 next semester. And this sort of seems like a weird one. All right, what's my assumption for factor analysis? Well, I want a factorable, if that's even a word, factorable R matrix. I want a matrix that I can actually factor analyze. Well, of course. So my assumption in factor analysis is that I want a correlation that I can factor analyze. Seems sort of circular. The idea being that if you have a bunch of items that are related, but they're related in very small ways, like they may have significant correlations, but they're all very tiny correlations, you're not going to get much out of it. There's not much there to really factor analyze. So you want to make sure you have correlations that are above 0.3, like they're large enough. And this is not a hard, fast sort of, it's got to be 0.3. You just need to have items that actually have real correlations that represent some overlap between those items. Because remember, you're trying to estimate common variance, shared variation. If the correlations are all really tiny, then that's evidence right there that they're not sharing very much variation. So you got to have a factor, a sort of correlation matrix that actually has some correlations in it that are of decent size that can actually be factor analyzed, and you can pull out the common variance from them. All right. Okay, so let's talk about extraction methods, and then we're talking about more of the same idea, sort of beating this dead horse, hitting the same nail over and over again. There are many. There are dozens at least, and in SPSS, I think they give you about maybe 10. I think it's less than that, more like 8 or something like that. All extract orthogonal sets of factors or components, if you're using PCA, that reproduce the R matrix. They all do the same thing. Some try to maximize variance, others try to minimize residual. So you have things like the MinRes is an actual extraction method, MinRes, which is short for minimum residual. Which is, I think, the unweighted least squares or something version that's in SPSS. Anyway, so they're all trying to do the same thing. They're all trying to do some estimation of the commonality during the first sort of iteration through. The only difference is components are the only one that assume 100%. Everything else tries to estimate it somehow. And even no matter which extraction method you use, if you try to look at the unrotated matrix, it's almost completely unintelligible, uninterpretable, unless you rotate first in some way. Okay. So now we're talking about factor analysis versus PCA, because up until this point, or a lot during this lecture, when I talk about factor analysis, I'm including PCA in there. It's just as another type of factor analysis, another sort of similar method. But here I'm differentiating those. Factor analysis has a family of procedures, including principal access factor, maximum likelihood, image, alpha, all these different versions. versus PCA, because there's that one big difference. So whenever you talk about factor analysis versus principal components analysis, factor analysis produces factors. We literally talk about how many factors are in a factor analysis. Well, with principal components analysis, they produce components, not factors, they're components. So there's difference in language. Factors cause variables, so there's a theoretical difference. Factors are causing the variables. Think about the direction of the arrows. It goes from the factor to the item. Where components or aggregates of the variables, they go from the items to the factors. They predict the factors are meant to sort of combine into the factor, into the component. Factor analysis analyzes only the variance shared among variables. That's a little bit strong. It's actually, it only analyzes the variance that it estimates to be shared among the variables. It's trying to get an idea of what the common variance is first, where PCA analyzes all the variance. Now, technically, they both are analyzing the common variance. It's just that FA tries to estimate it. PCA assumes that all of it is common, and that's why it analyzes all the variance. With factor analysis, the question is something like, what are the underlying processes that could produce these correlations? With principal components analysis, it's just, let's summarize the empirical associations, try to find patterns, and try to explain the patterns without any sort of theory sort of driving why the patterns would be there. So it's much more descriptive, much more, it really is more exploratory than, say, exploratory factor analysis is, but it's all part of the same basic idea. So again, conceptually, we have a factor would be driving the items, which is why the arrows are going this way. And up to this point, I made a point of sort of, in like canonical correlation, making sure the arrows went from the items to the variates, because they're not theoretically driving the items. It's just like principal components, they're just being combined. It's just a way of sort of trying to aggregate the items in a smarter way than just creating composites. So factors drive items. In PCA, the items are being identified as being related to each other and combined into a component. Factors drive items. Here, items are being combined into components without this theoretical belief that the items are being driven by the component. So you can sort of see it's a little bit odd. So I'm saying there's a mathematical difference, but there's also a bit of a I don't know, idealistic difference. And if it sounds like I'm trying to sort of denigrate or be negative about PCA, I'm not, even though I may come off that way. PCA is actually a super useful tool. It's just, it doesn't have this, oftentimes people confuse them and will interpret PCA the same way as factor analysis, and they shouldn't. This is much more descriptive, much more earlier on in your data when you're really trying to figure out what items are going together and trying to reduce things. This is much more sort of a data reduction only sort of process, where factor analysis gives you the data reduction process, but also tries to help you develop a theory about what is actually going on with the items and what's driving them and why these items are actually related to one another as part of some latent structure that you can't see. All right, so this fits much more into a theoretically developing or developed sort of structure, where this is much more sort of exploratory and descriptive. That doesn't make this better than this, right? It's just a different use, a different process, a different reason why you would do the two of them. And what I see too often, is that PCA gets far too overused. So in the literature, if you see someone do a principal components analysis and they present then this structure of components, and someone wants to sort of replicate that, what should happen then, as sort of DeVere mentioned earlier, you would think it would go to principal components analysis if it's really truly early on. Then it would move to at least a exploratory factor analysis, and then hopefully to a confirmatory model as it sort of goes through the literature. As seen too often is someone will actually present a PCA, somebody else will replicate it and also do a PCA, and then a third, fourth, fifth to 10th people also collect the same data and do a PCA again. So they keep descriptively exploring the same relationships as someone else has already found. It seems sort of silly. Dr. Plunkett and I, working with a graduate student a couple of years ago, we published a paper on this, where there was a scale that had been used and psychometrically tested over and over again only using PCA over and over again, and I couldn't quite figure out why that was. They kept just doing it over and over again. They found the structure with the some people there. People took it to different countries and used the same scale again. Did a PCA, kept doing PCAs over and over again. So we tried to replicate it using a sort of factor analytic framework, but there's also other corrections too because there's other issues. But it's more complicated than that. But one of the things that we kept noticing is every time we'd find someone that was trying to replicate or use the scale, they kept using PCA over and over again. Just really odd. It made sense the first time, maybe in the first couple times. After that, move on to like EFA or at least go to CFA or something, because it seems silly that they kept trying to like be. This is basically saying like, well, I don't know how these items are supposed to relate, so let's check it out. Let's see how they go together. Well, somebody else already told you this is how they go together. So why are you now back to like blindly looking for how they relate? It's a very weird process, theoretically. But all right, moving on. So here's where the difference comes in. You're going to start off with a correlation matrix. Right, that's everything. So let's go way back for a second. Back to here. Our main meat, the entree for this whole thing is this correlation matrix. Right? We're gonna give SPSS or whatever program you like, R, SAS, whatever, a correlation matrix, and it's going to do an eigenvalue deconstruction of this correlation matrix to get these, to try to go through and estimate the number of factors and what the factor loadings are. So we're starting here. Now, every correlation matrix you've ever seen has ones in the diagonal, right? So that diagonal line there represents ones because an item correlated with itself is 1, right? That works. So that's the typical correlation matrix has ones in the diagonal. And that in the eigenvalue deconstruction indicates that we're using 100% of that item's variance because it's 1. So PCA begins with 1s in the diagonal correlation matrix, which means it uses a typical correlation matrix the way that we're used to seeing it. FA begins by trying to only use the common variance. It does this by estimating the commonality values, like in some cases like the square root of the correlation, and it puts those values in the diagonal. So instead of having a regular correlation matrix with 1s in the diagonal, we're now putting the estimated commonalities in that diagonal of the correlation matrix to indicate to that eigenvalue deconstruction that something less than 100% is actually true, that the items actually don't share 100% of their variability. Because of that, it tries to extract all the variance at one time. It tries to treat everything as common, and therefore it's gonna extract more variance than it really should. And because of it also, all items get 1 to begin with, that's a way of saying that each variable is equal. It's saying that all the items we're going to start off by saying all the items are equally important in this scale and try to factor analyze that. Because factor analysis tries to estimate those commonalities first, it's going to only analyze the common variance, and it starts off by saying that some items have more shared variance than others. It actually starts off saying that some items are better or worse, have more variability to share than others in the very beginning. PCA can often lead to an over-extraction of factors and an overestimation of the commonalities are often inflated. The loadings are, because of that, the loadings are inflated and can lead to an over-extraction of factors, which is okay if you're going to test it. Like if you're going to say, look, I identified 6 factors in this scale, let's now collect some more data and see if those 6 factors sort of hold up doing a factor analysis. And you may actually then them dropping a couple of the factors and realizing, okay, we really have more like 4. There's nothing wrong with that. I'm not trying to say you shouldn't do PCA. I'm just saying the PCA by itself is going to be a difficult sell as a sort of final result for any sort of scale. And more work will need to be done to follow up with it. Outputs are more realistic, often smaller commonality values are estimated, usually results in far fewer factors overall. And you're probably thinking, Well, how can I make that claim? How can I make that outputs are more realistic? Just because they're smaller than PCA, why does that make them more realistic? And the only reason I could say some of this stuff is that there's been simulation studies. They've simulated items or simulated scales where there's a certain underlying structure. Let's say it has 4 factors, and they sort of generate the correlation matrix to sort of reflect that. And then PCA will find more than 4. FA will find the 4. Makes sense? So they oftentimes are a little bit are closer to being more accurate than PCA that will likely extract more than it should, because of that weird assumption of all variance is shared to begin with. Okay, so PCA leads to more factors, larger loadings, larger commonality estimates, where FA typically will estimate smaller commonality estimates. Smaller loadings, fewer factors, and it's typically closer to like the simulated number of factors that you're looking for in simulation studies. This typically gets closer, or this will actually tend to overestimate. All right. All right, so I've mentioned these. We're not going to go into a whole lot of detail about them because we could spend a lot of time just talking about the differences between how these things actually work. I will say that it's one of the things it ignores. Yeah, so the unweighted least squares is sometimes referred to as a minimum residual or min-res. So when I was in a doctoral program at UCLA, Andrew Comrie, who was an early sort of pioneer of sort of factor analysis like in the 50s, was still teaching there, and I took a class on factor analysis from him, and we had to do a factor extraction and rotation using his min-res approach by hand, which means we had to iterate through a bunch of times. And by hand, I don't mean necessarily by hand. I mean, like, we had to do it ourselves. So I think I used Excel to do it, but I mean I had to like iterate through and sort of figure out all the stuff. We had to actually calculate the angle of rotation, literally like using a protractor, and all kinds of stuff to do things by hand. I don't recommend ever doing that, but I did learn a lot about what a pain in the ass that process was. But we use this sort of minimum residual method here. So what are the differences? So the principal axis factors, we're going to estimate the commonalities with the squared multiple correlation. That is a typical, probably the most common exploratory factor analysis method, and maybe the close tie would be maximum likelihood. These two are probably the most commonly used. This one's sort of gaining popularity, especially in the last 20 years or something like that, because computers have gotten faster and maximum likelihood becomes more and more realistic. And it tries to use maximum likelihood to especially in the first iteration, to estimate what the loading should be to make the correlations as likely as possible. So it doesn't try to estimate the commonalities the first time in terms of putting them in the diagonal of the matrix. It just ignores those, tries to find loadings that make the data the most likely, and then those are the first estimates of the loadings. It then creates the commonalities from that, puts them back in, and iterates through, or something similar to that. I may have missed some steps in there. Unweighted least squares does something similar. It looks at just the off diagonals, ignores the diagonal to try to estimate what the commonalities would look like for the first iteration, puts those estimated commonalities into the second iteration, and then goes through the same after that until it converges. The only difference between unweighted least squares and weighted least squares or generalized least squares, they both do the same thing, except that generalized variables with larger commonalities are given more weight in the analysis. So more important, more relevant items are actually given more weight in sort of this sort of decision process going through things. When unweighted least squares, those things are ignored. It's just all the items are treated sort of equally when it estimates everything. There are other ones. I don't think so. There's like image and alpha and a bunch of other ones that are listed in SPSS, and there's even more than that if you actually go, look into it. There's a dozen at least different extraction methods, but principal axis factoring, maximum likelihood are probably the two most used anymore. I don't see people using much of anything else. So, go ahead. Well, yeah, I mean, we can get in some weeds about it, but honestly, if you're going to do maximum likelihood, this is a large sample. All this stuff needs a large sample no matter what. Maximum likelihood needs an even larger sample. Like all maximum likelihood things, it's a large sample estimation method, mainly because the estimates are assumed to be at the, like, if you had an infinite sample size, this is what the estimates would look like. So you have to have a large enough sample to be close enough to being this sort of infinitely large, asymptotic sort of estimate. So the only thing is, you really need more people, larger samples to do maximum likelihood. Otherwise, I don't know. For the most part, you should get relatively the same results either way, unless there's some. I don't know, unless there's some distributional weirdnesses that may impact maximum likelihood different than principal axis factoring or something like that I can't think of off the top of my head, but I think it's just sample size would be the main one. So, all right, rotation methods. After extraction, regardless of whatever method, whatever you pick your poison for whatever method you want to extract with. You like PCA, fantastic. You like principal axis factoring, good. Oh, it's all good. But you still got to rotate. So the second part of this is the rotation method. So after extraction, good luck interpreting results by itself. The rotation is used to sort of improve interpretability and improve utility. Utility oftentimes gets ignored with this, by the way, in this process. That when you create factors, yes, you want to be able to interpret them, but they should also be useful, meaning that other things should predict it, or it should predict other things for use in multiple regression or for use in other types of analysis. If it's not super useful for other types of analysis or other types of tests, who cares? What's the point of having that factor? I'll give you, for instance, if I created a unidimensional scale, a 5-question scale that measures depression, right? So and the factor analysis comes out great. Commonalities are large. The rotation, everything is a simple structure, whatever. It all looks great. But then I go to use it to predict something like anxiety or predict some other measure. It doesn't predict. It doesn't do what it's supposed to do. It's not very useful. So that's where, or if I want to use it to sort of diagnose people as being sort of high in depression or low, and it doesn't really correlate with clinical the clinical cutoff criteria for like clinical depression, it's not a very useful scale. So yes, I might be able to interpret it and it's clean, but if it's not useful, it has very low utility, then the scale is sort of pointless. Those items aren't very useful. So it really should have both of those things. Should be able to interpret it and be a clean, sort of, understandable factors and things, but those factors should also be useful for other purposes. That comes down to like convergent validity and other things where we go from reliability to validity, which is a whole different, related but different thing. An orthogonally rotated solution is mathematically equivalent to the unrotated, and I showed you that in the lab a little bit, where as we looked at the rotated matrix, I could still sum and square the loadings and get the same commonality. So it actually holds the commonality constant, rotates things around, sort of spreading the variance around from one to the other, but mathematically sort of stays equivalent. If you have stable and large n, you should get the same result regardless of the type of rotation that you choose. In terms of if it's orthogonal rotation, you should get a similar result. If it's oblique, you should get the same result. But this is from the textbook. Their goofy 4-question factor analysis that they do. That's sort of goofy, but here it extracts out the first factor. So if you plot these are different. These are the items sort of projected out as sort of vectors in space. These are the points. Factor 1 comes in and is the first one in the eigenvector eigenvalue deconstruction. It gets put in here. Factor 2 gets put in sort of orthogonally to the first one. Factor 1 explains the most variance. Factor 2 explains the leftover variance. And by simply, you notice that this is far away from here and far away from here. So both of these points are actually pretty close to factor 1, but the 2 points around factor 2 are actually kind of far away. If I turn this ever just slightly, rotate the factors, keeping them orthogonal, rotate them slightly, I've now increased the loading between, for cost and lift. I've actually made those, increased those. I may have sort of reduced some of the loadings here and sort of shifted the variability of these loadings to these loadings. This is what a varimax or a rotation would do. It would try to take some of the variability from the first factor and shift it over to the variability in the second factor, so that these loadings get larger, even though these loadings get a little bit smaller. So sort of shifting, as I think I said, it's like the Robin Hood, right? Sort of stealing from the rich and sort of giving to the poor to sort of even things out. It's trying to maximize the variance of the items across the factors. Okay. So rotation, all we're really doing is taking where those factors are, moving them a little bit. This is a 19-degree rotation. Right, so it's literally figuring out that if I shifted this 19 degrees, I can actually maximize the variance of factor 2, but have very little impact, if any, of sort of the variability on factor 1. All right. So if none of that makes sense and it seems confusing about trying to rotate things geometrically, just think rotation is a way of maximizing interpretation. We're trying to make it so that factor 2 is easier to interpret, where under this category, factor 2 is not very interpretable. It seems like factor 2 is not doing very much of anything. Factor 1 explains a lot, factor 2 does almost nothing, but by rotating this way, factor 1 is still doing quite a bit, and factor 2 now makes a lot more sense, to where the first factor is because depth and powder, if you think about skiing, depth and powder actually relate to each other, right? So if you have more snow, it's oftentimes more powdery. It's not packed, it's not packed in. So depth and powder is a sort of a snow factor, and cost and lift have to do with the sort of the facilities, like how good fast the lift is, how much it costs for a lift ticket, or other things at the facility. So by rotating this so that the snow factor sort of falls in between those two, I've actually made the facilities factor a lot more interpretable and a lot more meaningful. So that's what rotation does. It tries to So there's more than two. So right now, we can think about it on a two-dimensional scale, sort of rotating this way. Right, so if you imagine now there's a z-axis this way, right, so there's one coming at you now, right, it's still the same thing. If I'm rotating orthogonally, I'm still going to be rotating them in a way that keeps them orthogonal to each other. Make sense? You could, but because this example, I think, only extracted two factors, which is why there's no z-axis. But yeah, it would now be also rotating. So instead of rotating, this way and this way, it's also rotating this way too. And keeping. Yep. As long as it's an orthogonal rotation, the orthogonality of, if you have 30 factors, it's keeping all 30 factors orthogonal while rotating in 30 different dimensions. You can rotate. You can rotate them all. It's just we can't picture it beyond 3. It's all mathematically being rotated. It's just we can't picture it. We don't know what 4 dimensions or 5 or whatever it looks like, right? So this is, so it's easy to think about rotating in sort of 2 dimensions, and even with 3 dimensions, you can sort of see it sort of be rotating this way and keeping everything sort of together, right? You can sort of rotate all of them around. But beyond that, we can't even picture it. But it's still mathematically rotating in the same way. It's just we have no conception of what that would look like. All right? Moving on. Got a lot to cover. So factor extraction is sort of equivalent to sort of putting the factors and creating the coordinate planes around the points in space. So the factors are those axes, like in these pictures, obviously. The length of the line from the origin to the variable coordinates is equal to the commonality for that variable. The hell does that mean? This is speaking in geometric terms. It's something like if you were to plot a line from the origin between the two factors, the point where they cross. So actually, let's do it here since they're not together. You take the point where these two cross, right, and actually to do a line out here. The length of that line is relative to the commonality on that factor, right? So these, right, are representing the commonality somehow. Okay. Make sense? That's what that says anyway. The length of the line from the origin to the variable coordinates is equal to the commonality for that variable. Orthogonal factors are at right angles, which is what we have here. And also, I don't think if I even mentioned it here, but something like if you actually wanted to look at the loadings, you could drop, if you drop a line orthogonal from the point orthogonal to the factor, like this, and the same thing from here to this factor, like that, that would tell you, it's like, I think that gives you like the loading or something. You can actually then compute the loading from that as well. There's all kinds of geometric terms that are ways of looking at this that actually correspond to a lot of what we do. So I want to point out here, though, that we used to teach Psy524, which was all the geometry and calculus and stuff behind everything we talk about in this class. I want to make a note here that I don't teach that class because I don't know any of that crap. Like, I know some of it, but the mathematics, my background's not mathematics, my background's in psychology. And I sort of shifted over to quant. But, you know, at one point I took 520 and I, you know, got an A in the class or whatever, but there's no way I was like, I'm not teaching that class. No thanks. I'd rather teach 534, teach latent variable modeling, than teach the geometry. Literally, the book that we used in that class was called The Geometry of Multivariate Statistics. Written by, crap. I took the guy's class at UCLA and I can't remember his name top of my head for a second. Anyway, it doesn't matter. But it was a lot of these kinds of pictures trying to explain how the geometry and calculus, like derivatives and all those things, sort of relate and how those things get, are used in multivariate statistics. So, I'm not going too much into that detail because it's not a strong suit of mine. So I'm going to talk about the application stuff instead. So this is like the closest we get. Length of the line from the origin to the variable coordinates is equal to commonality for that variable. It's about as far as I'm going to get into the geometry of multivariate statistics there. Okay, maybe not. Maybe there's more. Factor loadings are found by dropping a line from the variable coordinates to the factor at a right angle, as I just mentioned a second ago. So we can actually, if everything's plotted out and plotted out to scale, we could actually compute the commonalities and the loadings based on the geometry of those points in space. And as you rotate the factors, you can then recalculate with the loadings and the commonalities. Actually, commonalities should stay about the same, just rotating away where the factor loadings are. So that's why, I mentioned before that as we rotate orthogonally, the distance from this origin to that point is not going to change. As I rotate these factors around, the distance from that point to here, is the same as this point to there, right? It doesn't change, so the commonalities stay constant. But as I rotate away, if I drop a line from that point to this line or that point to that line, I'm getting different estimates of loadings that then square up to actually equal what the commonality is across the factors. So rotating actually changes the loadings but keeps the commonality intact, which is why rotation works. It's mathematically equivalent, but we're actually increasing interpretation by rotating around. So that's what this is sort of saying. Here, repositioning the axis changes the loadings on the factor but keeps the relative position of the points the same, which means that the commonalities stay the same, and that's why we can rotate orthogonally and everything. It still adds up to the commonalities and things. Awesome. Let's get away from geometry. Okay, orthogonal versus oblique. Orthogonal rotation keeps factors uncorrelated while increasing the meaning of the factors. Oblique rotation allows factors to correlate, leading to a conceptually clearer picture in terms of interpretation sometimes, but it could be more of a nightmare when it comes to explanation. I'll talk about that in a second. So, because instead of being one loading matrix that is rotated, you're now sort of separating out the one loading matrix into two additional matrices called the structure and the pattern matrix, which make things a little bit more complicated, but oftentimes it's what is necessary to really get an idea of what's going on in the factors. So here are the most common sort of methods for rotation. Varimax is by far the most common, period. So most of the time when someone starts off doing exploratory factor analysis, even if they think their factors are correlated, they're going to start off doing Varimax first. Right, it's the most popular because if Varimax can get you simple structure, then it's the easiest one to sort of interpret. It's the easiest one to deal with, so they'll do Varimax. Simple structure by maximizing variance of loadings within factors across variables. We're trying to maximize the amount of variance in each factor across variables. So spreading out the loadings across the factors to try to maximize everything. And again, it's like sort of a spread the wealth, right? Makes large loadings larger and small loadings smaller. That's actually not true often. It seems backwards. It actually will oftentimes take variance from larger loadings and spread them out to smaller loadings for factors that you are keeping. So it does make large loadings larger and small loadings smaller. This is sort of oversimplified. So it does do this for, if a loading is small, like negligible, it'll make it even closer to zero. If a loading is large, it'll actually help to sort of differentiate those. But it will sometimes take medium loadings, make them larger, and it's just trying to spread out the variability across items. So this is a little bit oversimplified in terms of its statement here. Not quite just doing that all by itself. It's doing a little more than that, but this is better. It spreads the variance from the first largest factor to other smaller factors. So let me think about that for a second. So it's spreading the variance from the factors with larger sort of squared correlations, like the larger eigenvalues, to those smaller ones. And to do that, it's taking loadings. Yeah, so it's not just making large loadings larger and small loadings smaller. It's more complicated than that. That's a little oversimplified. It's trying to spread the wealth across the factors. It's when you extract, say, 4 factors, the first one's going to have the most variance, second one is the next, third next, fourth next. It's trying to take variance from those larger first couple factors and rotate in such a way where the variance can sort of spread out and tries to equalize or maximize the variance across those other factors by taking away from larger factors and giving it to smaller factors. It should help to differentiate between which items are going with each factors, which is why this sounds like it's correct. Makes large loadings larger and small loadings smaller on the items, but it's still a little more complex than that. It's trying to just make everything clearer, what items go with what, and while trying to spread the variance across the factors. All right. There's other ones that don't get used quite so often. So quartermax is the opposite of varimax. Opposite of varimax, simplifies variables by maximizing variance with variables across factors. It's now trying to maximize the commonalities, the variance of items by rotating across factors. That's not what people typically want to do. Varimax works on the columns of the loadings matrix. Quartermax works on the rows. It's not used very often. Simplifying variables is not usually a goal. We usually are trying to understand them. We actually wanted to make them more viable. This is actually sort of working to make them less viable and make the people's or the responses across items sort of more important than the factors, which is very strange. So this is there. It's a thing that people use, but it's strange. It doesn't get used very often. So the opposite of sort of maximize variance across the items, not the factors. Anyway. Equimax is a hybrid of both. It's trying to maximize both the factor variance and item variance simultaneously. Again, not very popular. It's not typically the goal what people want to do. Not trying to maximize in that way. We're actually trying to spread out the variance of the factors across so that we can actually interpret them. This doesn't make interpretation easier. It actually can make it more complicated, make things more messy. That's why it's typically not used. But those are like the 3 orthogonal rotations, this one being the one that's the most popular overall, and it's also the one that pretty much gets used, especially as an orthogonal rotation. These don't get used very much. As for oblique rotations, there are 2 that I'm mentioning here. That's about, yeah, I just mentioned these 2. There's one called direct oblumen. So if you would use this or Promax for 2 different, well, for the same but potentially different reasons, for similar but different goals. If you think your factors are correlated, you can start off with that assumption that they're correlated and let them start to correlate right away. Right? They start to correlate from the very beginning, and you can control the amount of correlation by this thing called by this thing called gamma. Values near -4 are essentially orthogonal. If you leave it at 0, which I think is the default, it leads to mild correlations. And if you leave it at 1, it allows them to be as correlated as you want. So it starts off with the idea, it starts off rotating factors independently from the beginning. Everything's being rotated on its own. So it allows everything to be correlated. The difference between that and Promax is that Promax starts with Varimax. Right, so it starts to rotate orthogonally first, and then gets as far, does as good a job as it can, and then rotates obliquely. So it starts off orthogonal, leads, and then changes to an oblique rotation to improve simple structure. So orthogonal loadings are raised to powers in order to drive down small loadings. Simple structure is reached. It's an easy and quick method, which is why people liked it, because they could get as far as they could with orthogonal and then let things go oblique, which means that there was less iterations to get there. It also will minimize the amount that the factors are allowed to correlate. So it keeps the correlations sort of at a minimum while trying to find simple structure at the same time. This one's probably, if you're going to do an oblique rotation, this one's probably the one that's sort of used more often. It's just like if it's oblique, to start that way and start to rotate that way. But you will see Promax used still when people are trying to when people think that they actually have orthogonal factors, but when they use Varimax, they still have complex loadings and it's still messy. So they switch to Promax to sort of allow it to go, correlate a little bit, but without going crazy and making all the factors super, overly correlated with one another. So this is a way of sort of going just a little bit beyond Varimax to sort of allow them to correlate a little bit and increase simple structure. So this is still used. I think I want to say that even at some point, Tabasco and Fidel, I think even recommend this one as like as a method that they prefer or something. But for the most part, this one, if you want the factors to correlate, use direct oblumen. If you're trying to avoid correlation but need it to get simple structure, then Promax is probably the way to go. So basically Varimax plus a little bit of correlation. All right, so we'll stop here and get